Hi everyone, Mr. Allen here. I was asked to go over question 10 here from the optimization problems. Now I posted a solution previously, but maybe talking through it will help as well. If we look at the question, hopefully we understand it, and obviously the word inscribed may be something that's not super familiar, but Google will tell you exactly what that means. So essentially it means we have this situation. The rectangle is being drawn inside of a semicircle. It tells me that the length of the rectangle should be placed along the diameter and that the radius of the semicircle is 10 units. So that is to say that this distance is 10 units. Now, anytime I do these problems, I'm always going to be given a piece of information that I want to start with, and I'm always going to be given a value that I'm trying to maximize or minimize, optimize essentially. And so I'm told here the radius is 10 units. I'm told I want the largest area. So I know that I'm going to be working with this radius to establish some kind of a formula that I can then make use of in determining the area and allowing me to eventually take the derivative of the area of a rectangle. So the real key here is to recognize that if this is the radius of the circle, I need to make use of that inside my rectangle somehow. And well, if we rotate along the edge of the circle, we see that the radius forms a diagonal that basically goes from the midpoint of our rectangle to the corner. That of course allows us to establish a right angle triangle in here. We're going to have a hypotenuse of 10. I'm going to call this the height of the rectangle. I'm going to call this the base of the, the base of the triangle, the height of the rectangle and the height of the triangle. And now I have the opportunity to make a Pythagorean theorem. B squared plus h squared will equal the 10. And so 10 squared equals b squared plus h squared. In all cases now, I want to use the formula that I've established from the given information to rearrange and isolate for a variable. So in this case, I chose to isolate for b, not for any real reason except that that's what I chose to do. Now, the second thing, of course, is I want to work with the area. And so the area of a rectangle is what I'm going to be looking at next. And the one key here is to recognize that this distance, what is my length essentially of my rectangle, will be 2 times the value of b. So when I look at the area of the rectangle, area is length times width. The length is 2b, and the width is what I originally established as h. Now, having done that, I can use this, I can use the fact that I isolated b here. So this is equivalent to b. I'll substitute that in for b so that I now have an equation dealing only with h's. And just slight rearranging here, 2 times the h, rewrite this with an exponent of 1/2, will allow me to now take the derivative of that value. And so when we do the derivative, a prime equals, and I won't talk through this, but you can sort of figure it out. The derivative of 2h is just 2. Leave this part alone, plus, so I basically used the product rule here. Leave the 2h alone and take the derivative of the second term. I slightly modified it here. It's partly covered, so that's minus 2h squared over. So this was to a negative exponent. It becomes my denominator. And then in order to do a maximum, once I have the derivative of the area, I need to make that area equal to 0. And now I'm just basically rearranging the equation a little bit. So eventually we get down to h squared is 50. H is technically plus or minus root 50, but of course, because I'm dealing with a real-world problem, I know that it's not going to be the negative value. So the height is 7.1. When I plug that back in to find b, I find that essentially this was, well, h was root 50, so h squared is 50. and so B ends up being 7.1 as well. Last thing to realize and to recognize is that B was only half of the length of my rectangle, and so the actual rectangle will be 14.2 by 7.1, or approximately 100 square units.